welcome everybody to lecture 16 of the analysis of algorithms, CSE 548. Before we start class today, let's start with, are there any questions, okay, about anything to discuss? Okay, now there are a couple of announcements I'd like to check about. First of all, the programs are due today, which is one reason why I see people scrambling to get into the room a little late. The people are probably working on their programs. Programs are due today at the beginning of class. If you wanted your extension, you're free to use your extension on the program. So that's fine. Okay, that's assignment like any other assignment. If you, I'm going to want everybody to turn in a printout with their, basically the program code and the results of their runs. Okay, that's sort of what I wanted to see if, as being turned in. Okay, if you have any problems with that, let me know. Now, electronically, I'm going to want to receive the programs of anybody who's interested in participating in the contest and thinks they have a chance to be the fastest program of either the undergrads or the grads. So let's take a quick poll here just to see how people are going to set sort of standards, and then we'll see how we're going to hand that. First, among the undergraduates, how many undergraduates are here? Raise your hand if you're an undergraduate. Okay, a bunch of undergrads. Okay, how many of the undergrads have programs that go beyond 10 vertices? Okay, how many of the undergrads go beyond 10 vertices, it looks like? Okay, how many undergrads go beyond 15 vertices? Okay, a few more. Okay, how many undergrads go beyond 13 vertices? Okay, if your program goes beyond 15 vertices or beyond, I want you to email me if you're an undergrad. If you've got a program that can do 15 vertices, okay, or very close to 15 vertices, I want you to email me your programs so I can run them. Okay, that looks like that's going to be the standard that it's going to take to win the undergraduate prize. Among the graduate students, how many graduate students are here? Raise your hands. Okay, how many graduate students have programs capable of doing 10? Okay, a bunch. Okay, how many people have graduate students have programs capable of doing 15? Okay, a bunch. How many people have graduate students have programs capable of doing 20? Okay, it looks, okay, how many people have capable of 25? That's where things are weakening out. If you're a graduate student and you have a program capable of doing 20, I want you to email me the program. Okay, and that will be where we will draw the competition from. Okay, so that looks like the cutoff. And if for some reason every program here fails, then we'll go back there. So I want to see any programs that are capable of doing this. I won't be able to run them until presumably Thursday, possibly after class. So you have till Thursday morning to get me your program, okay, if you're capable of doing 15 as an undergrad or 20 as a grad. Yes?
Do you want the source code or the executable?
I want the source code. I want you to email me the source code, okay, and instructions for how to make it and stuff like that. Yeah?
If you hand it late, you're disqualified.
If you hand it, I'll tell you what, if you email me your programs by Thursday morning, okay, you're eligible for the competition. If you're an undergrad and you still want to keep tweaking your program to get to that standard, 15 is clearly what it's going to take to be competitive. Okay, if you can get it there by Thursday, I want to see your program. Okay, same thing for the grads. If you get beyond 20, then we can talk. Yeah.
Can I use my 1-week extension to do some further?
You can use your extension to tweak further for extra credit, but the competitions will be run with the programs as of Thursday morning. Okay. Question. If you don't have a printout and you sent me, you know, either send me an email or throw a printout in my mailbox as soon as possible after class. Okay. Some of you have mailed me things. Okay. If you haven't, I want to see the printout. It's easier to grade from the printouts. So send printouts for get me printouts of your program and runs that you've succeeded in making. That's how we're going to prefer to grade. If we need the source code, if we have some questions about your program, we will get in touch with you about that. Okay. Any other questions about the programs? Okay, so we won't have the results in time for next class, but I want to see all the programs by then. Okay, any other questions? Yes. Okay, question about partners. Now another thing today, I'm giving out homework 4, which is the next the next regular homework assignment. Some people have had problems because their partners have vanished for whatever reason. How many people here do not have a partner and would like to have a partner? Raise your hand if you don't have a partner and would like a partner. Okay. Okay, raise your hand. Okay, wait, hold on. Okay, there I see a match over here. You don't have a partner, correct? No. You don't have a partner, correct? You guys know each other or look at each other, okay, and make plans after class. Okay. Any other questions? Okay. Graduate projects. Several students have turned in graduate project proposals. If you have, I've commented on them. If you haven't gotten back your proposal from me, get it back from me. I have them here. Okay. If you haven't turned in a proposal, turn something in writing just so I know who you are and what you're doing and have any comments about that. Okay? Any questions? Final bureaucratic thing is that I'm going to have to leave office hours a little early today, so I'll be there until about 2 instead of 2:30. So if you have questions, come by a little early today or send me mail and we'll make an appointment. Okay, any questions? Okay, today's problem of the day asked the following question. Okay, given a efficient algorithm to test if a graph is bipartite. Okay? Well, what does it mean if a graph is bipartite? Okay? A graph is bipartite means that the vertices can be colored, okay, as either red or black or red and white or whatever how you want to call it. Okay? That the vertices can be colored in 2 ways such that no edge links vertices of the same color. Okay? Equivalently, you have left vertices and right vertices, and every edge goes from left to right. Okay? Algorithmically, how could we test whether a graph is bipartite? The key insight here, okay, is suppose we take one vertex and we color it red. Okay? If I have a choice between coloring my 2 vertices, they're either red or black. Once I color one vertex red, okay, what color does every vertex that has to be adjacent to it have to be? Black. There's no choice about it. Okay, everything is forced. Okay, so if you have a red vertex, every edge from it has to describe a black vertex. And so basically what we can do is walk from our one chosen vertex to every other vertex and color the things in the order that they're received. So for example, these now have to be colored black. Okay. Oh, you mean what? You don't like you don't like the color difference. Okay.
On the big screen, there is no color difference.
Oh, there is no color difference on the big screen. Okay, fine. Okay. Well, okay. I mean, so these would now get colored black automatically. We now consider every single edge. Every single edge is going to have 2 properties. If we start from one vertex that's colored, all adjacent edges will either be adjacent to a vertex that is black, or it will be a vertex that hadn't yet been colored, in which case we can make it black, or it will be adjacent to a vertex that is red, in which case we've got trouble, because that's an edge between 2 things that are the same color. Since when we start from any one vertex and only do the colorings whenever we're forced, that will give us a way to tell whether the graph is bicolorable. Okay, because everything is going to be forced once we pick one vertex in a connected component. Okay? And it doesn't really matter if we pick the first color as vertex as being colored red or black, because it's just a question of reversing left and right. Okay? So the basic thing that we need to be able to do is simply search through all the edges, okay, or traverse the graph starting from one vertex. You could do that in lots of different ways. Okay? Starting this class, we'll talk about breadth first and depth first search, which are good ways to do it. Okay? But even without that, the important thing is that the decisions are forced. Okay, and so once you start from one, walking to the others, okay, so long as you discover all edges, visit them in the systematic order, you can color it that way. Okay, and in fact, we can walk over all the edges in order n plus m time, where n is a number of vertices and m is a number of edges. Okay, any questions about this algorithm? Why it's got to be correct? Okay, and why, as far as why it's efficient, it should be efficient that if you walk on this thing in the proper order, you only will need to visit each edge and vertex a certain number of times. So that's where the efficiency will come from, but I'll talk more about that when we talk about depth first search. One final thing I'd like to observe about this problem is when might it come in? Why might we care about bipartite graphs? Okay? And it turns out in a lot of applications, okay, graphs turn out to be bipartite. Okay, meaning they can be 2-colored. Okay? And once they're 2-colored, there's lots of problems that become easier algorithmically on them. So if you have a problem where the graph that underlies it is bipartite, that's a useful thing to know about. Okay? And bipartiteness often falls out naturally from certain applications. So for example, we were talking last class about the had sex with graph, okay, where the vertices are people, and there's an edge between two people if they have had sex, okay? If the had sex with people, had sex with graph, was bipartite, what does that tell you? Okay, under what conditions could that graph be bipartite? Okay.
Probably if there were no gay or lesbian people.
No gay or lesbian people in that thing. Why? Because in some sense the two parts we're talking about, again, male and female parts. Okay? And if we're talking about a purely heterosexual group of people, all the edges would be between men and women. Okay? And again, that's just sort of an example that these kind of things, when you can recognize certain applications, bipartiteness usually it occurs for a logical reason. Okay, where it emerges from the application for a logical reason. Okay. Another example, okay, of bipartiteness, okay, might come in, or why it might be useful to think about things as a bipartite problem. Suppose you were given the following problem. Okay. Suppose you were given, you were trying to arrange, let's say, 2 sessions of a movie, okay, or it's two meetings, okay. You want to break your group into 2 groups, and you have certain pairs of people who you know hate each other, okay. It would be a bad thing if they were in the same room at the same time, okay. How would you schedule the people to be in different rooms, okay, so that no 2 people who hate each other are in the room simultaneously, okay? How would you model that as a graph problem? Okay? What would the vertices be?
People.
The people. And what would the edges be?
They hate each other.
They hate the other groups. Okay? And what do we want to do? We want to find a way to partition the people into groups such that all hatreds span the 2 groups and are not within the 2 groups. Okay? So that's an example of a scheduling problem that really just turns out to be testing bipartiteness. Okay, and it's important to think about, to realize that somehow to relate applications to these kinds of problems. Because most of the time when you're applying graph algorithms, you're not trying to come up with a whole algorithm from the beginning. Usually the way graph algorithms get used are, there's a small number of things that we know how to do, we meaning the people who, let's say, may have written the textbook, or the algorithm specialists, or you who took the class. Most of the time what you really need to do is figure out which one of these is your problem, okay? And that's the modeling issue, and that's really what you got to be aware of. Any questions? Okay? Now, the one exception to that, the one real exception, the case where, let's say, graph algorithms are simple enough that you may be called on to devise your own, turn out to be problems that are really just variations of graph traversal. What is graph traversal? Well, fairly often we've got a graph, okay? We want to visit every edge and vertex in the graph. Why might we want to do that? Well, for one, every edge and vertex. You might want to count how many edges there are. You might want to test whether the graph is connected, okay? Namely, if it's all in one piece or not, okay? And the way that you can tell, for example, if a graph is connected is you start on one vertex and walk everywhere that you can possibly walk from that vertex. Anything you can't get to has to be in something that's not connected to where you are. So the basic property of testing whether something's connected is testing basically whether you can walk from one place to another. So the fundamental problem, maybe the most fundamental problem to building a graph algorithm, is knowing how to walk through all the edges and vertices. Okay? And there's 2 different goals that we're going to want to solve in doing this. First of all, we want to make sure that we walk through the graph efficiently. Okay? That we don't visit any edge or vertex too many times. Okay? Second of all, we want to make sure that it's correctness. It's correct that we visit every edge and vertex at least once. Okay? And while walking through a graph is really a simple problem, it's not a very simple problem. There are complications. These things, these efficiency and correctness issues, are maybe a little more subtle than they may appear at first. And the example of this that I would have is walking in a What's a maze? Well, you've probably seen a maze. I probably should have a drawing because I probably can't draw it very easily. A maze is a pattern of, sort of caverns and things like that, different alleys. And your goal is somehow to walk in at a particular point. Let's say you walk in here, and your goal is to get out here. How do you find whether there's a path from here to here? Okay? Solved by hand, typically. Okay? Why is that? Because, well, it's potentially confusing. There's lots of different ways you can go. And okay, there are various stories from Greek mythology about where people get trapped in mazes and die, so it could be a serious problem. Okay? But my claim is maze traversal, walking out of a maze, can really be thought of as walking on a graph. What is the underlying graph when you've got a maze here? What are the vertices of the maze? The junctions, okay? So, for example, here would be a vertex, because here I've got a choice of going this way or that way or that way, okay? Here would be a junction, because I have a choice of going actually there, there, or there, okay? Whenever I have a decision to make, that's going to be my vertex. Whenever I have an edge, what are my edges going to be? The corridors. That's what my edges would correspond to. Now, what is the efficiency issue? What is the efficiency problem in walking in a maze? Why does it take a long time for people to get out of mazes? Okay?
Like you might end up walking the same.
You get lost. You keep repeating yourself. You get into an infinite loop. Okay? So you could say, well, look, oh, this is a nice way. Why don't I go here? And why don't I go here? And why don't I go here? And why don't I go here? Okay, you're trapped. That's what Greek mythology tells you. The thing that you have to do is to make sure that you don't get stuck. For efficiency, you have to make sure that you don't get trapped and that you don't visit the same place too many times. That's the key efficiency issue. What is the correctness issue? You have to make sure that if you're going to find there may be only one way out of this maze. In order to make sure you find it, you have to systematically visit every single vertex and guarantee, that you will have a strategy that will visit everything. Because if not, again, you may miss the exit and you will die. Okay? That's the problem. Correctness and efficiency. Okay? And it's important to see what the problems are when you think of it in terms of as a maze. Okay? Any questions about that? Okay? So what are we going to do? Okay? How do we get out of, what is our idea for quickly getting out of a maze? The basic idea is marking vertices. Okay? The big problem that we had as far as efficiency was we didn't want to get trapped visiting the same place over and over again. The way that we could avoid doing that is by marking each vertex when we visit it. Okay? And keeping track of how thoroughly we have explored that vertex. Okay? So the key idea is we're going to maintain two flags, or two states. Okay, actually it's three states, two flags, associated with each vertex. Okay? The first issue is, have we ever been to this vertex before? Okay? The second thing is, have we completely finished exploring everything we could possibly learn about this vertex? Okay? Because let's think about what the problem is at a maze. Here we go back to our maze. We're walking in our graph. Here we suddenly discover this vertex. There's several possible branches going out of the vertex. We could go here, we could go there, we could go here, we could go there. First time we get to this point, we have discovered it. But in order to make sure we explore it thoroughly, we're going to have to explore every possible branch getting out of there. Okay? So realize that there's a limbo state between when you first discover it and when you've completely checked everything out. The discovery involves visiting each one of the edges. Okay? I mean, that's really what exploring it means. Discovery means the first time we know that there's a vertex there. Okay? And so there are two different issues. We're going to have to maintain two different states. Okay? So the key thing is we need to maintain The two flags, is the thing discovered or not? Okay. Then we also need to maintain a data structure which will contain all the vertices that we have discovered but not yet completely explored. Okay. As with the maze, we're going to start from a single vertex, which is our entry point. We are at some point in the maze to start with. At the beginning, we have discovered our starting point, because we know that we were here, we discovered it, but we haven't explored anything yet. And our goal is to start from this one discovered vertex, everything else undiscovered, and we'll end when everything is completely explored. How do we do it? Well, when we look at a vertex, we're going to look at every edge going out of it. Okay? Every edge we go is either going to go to an undiscovered vertex or a discovered vertex. Why? Well, there's nothing else it can go to. Vertices are either discovered or undiscovered. Okay? When they're completely explored, that meant they've already been discovered. If we discover a previously discovered vertex, we haven't discovered anything. Okay? But that's fine. If we discover an undiscovered vertex, then we know that we've got to do some work there later on. Okay? And so we have to store that. We mark that vertex discovered and add it to the list of things we're going to explore. Okay? The point of this, the reason why efficiency is going to fall out of it, and this is important to see, is that when we look at an undirected graph, okay, even in a directed graph, every edge we're going to look at most twice. Why are we going to look at each edge twice? How many vertices does an edge touch? 2 vertices. So potentially we're going to discover the edge. Once we're going to go to this vertex. Now we discover this vertex. We're going to go and explore this edge at some point. That vertex before may or may not have been discovered. If it hasn't been discovered, we're going to discover it. Later on, we're going to explore this vertex. When we explore this vertex, we're going to go look at that edge. Okay? Or we could look at the edge going that way. Each edge is going to be looked at either coming and going. Okay? Each edge will be looked at twice. Okay? Maybe, conceptually looked at twice. Okay? Question. Can't you mark the edges instead of vertices? In principle, you could mark edges, okay? But there's no reason to mark edges, is I guess the way that I look at it. What's the problem with visiting each edge twice? Okay, going from both sides, but that's not really a problem, because you'll know when you've done it. Think about what's going to happen when you discover a vertex. You discover an edge. Here we have a vertex. We've just discovered it for the first time. We walked over here. There's an edge going to it to an undiscovered vertex. When we expand this edge, when we explore this vertex, we are going to go to discover this vertex. Okay? Originally, this edge went from a discovered vertex to an undiscovered vertex. Therefore, we discovered this thing. Now we may either discover it or completely explore it. I don't know, depending upon how we do our search. But later on, we're going to look at this vertex, and we're going to explore this vertex. And when we do, we look at its edges. Its edge now goes from a discovered vertex to another discovered vertex. So we know that this guy was not undiscovered. We've already visited this guy. And so there's really no confusion about the state of this edge. Okay? The edge is undiscovered when one of its vertices is undiscovered. Okay? And it's been discovered when both of its vertices, well, actually, when both of its vertices have been explored properly. Okay? So it turns out the important thing is to maintain the state of the vertices. There's no problem with walking over each edge twice. The problem is if we walked over each edge 1,000,000 times. Okay? Does that answer your question? Or? Okay. Questions? Okay? So what is the correctness? Again, the important thing to realize is that there's a correctness issue. If we do the traversal in this way, keeping track of everything we've discovered, and then eventually exploring everything that we've discovered, we will eventually visit every single vertex and edge. Why is that? Suppose it didn't. Suppose that if we have a connected component, and there is some vertex out here, which in the course of our traversal, we start walking from here. Suppose our algorithm was incorrect. That would mean we never discovered this vertex. Well, if the graph is connected, there's going to be some edge between a vertex we didn't discover and a vertex we did discover. When we look at this discovered vertex, at some point we discover this vertex. When we discover this vertex, we put it on the list of things to do to explore. When we explore it, we're going to go through all adjacent edges. One of those adjacent edges is going to have to go to this vertex. And at this point, we're now going to say, aha, we've discovered it. So by keeping the track of everything that we've discovered and making sure we explore everything we discover, we will discover every vertex. And since we're going to explore all the edges from every vertex, that guarantees us we will walk over each edge. Okay? That's where the correctness of this is going to come from. Okay? Any questions? Okay? Question?
Use just one variable and recursively backtrack through the whole.
Okay. There may be a lot of there are different variations that some of these variations will work and some of these variations will not work. Okay? It's a question of being careful. Okay? The variation I'm going to talk about is going to work. Okay? And I wouldn't mess around with it too much unless you really feel you understand things. Okay? There are different ways you could do it. For example, you don't necessarily need to maintain 2 flags. You could maintain 1 flag with 3 states, let's say. Okay? And there's different ways. But the tried and true formula is very efficient. It is correct and efficient. Okay? And for that reason, there's no real reason to mess around with it. Okay? You want to make sure you visit everything, and you want to make sure you only visit it twice. If you do that, there's no benefit to visiting it 1.5 times. Okay? Or once. Okay? It's more important that we just make sure it's correct. Any questions? Okay? Now, in the scheme that I've specified, the only thing that's really not been specified that turns out to be an important distinction is the order in which we store the vertices, okay? Or the order in which we keep track of what work we still have to do. Namely, the vertices that have been discovered but have not yet been completely explored. Okay? And there's 2 different ways that you can do it, okay? Depending upon whether you store them in a stack or a queue. Okay? In a queue is, remember, a data structure that stored things in a first out, first in order. First in, first out order. If we do it that way, the next vertex that we explore is going to be the oldest unexplored vertex in our system. Okay? When we do that, that's a breadth-first search. Okay? Because in some sense, we're starting from some vertex. We're going to explore its neighbors, keep track of them, then explore the nearest, the oldest neighbor in our queue. This was the first one, second, third. We now explore this guy. And that brings us out a little further. We discover these. The next vertex we explore is going to be this thing, the oldest thing in our queue. And that's sort of a breadth-first search because we're radiating out from our central vertex. The alternative is going to be if we stored the things in a stack. Okay? And a stack is going to be a case where we store them in a last in, first out order. Okay? How would we visit a graph in a stack? Well, we've got one vertex to start with. It's got several children, but the one we're going to explore first will store these guys in our stack. But the ones we get to first is going to be the last one we stuck in there, which might have been this one. If we push, 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 pop, we now discover all of its children. The last guy we put into the stack is the first guy we explore. So we pop that guy out. And so there's a difference in the behavior. We store them in a stack. We wander away from the vertex that we started very quickly, in principle. Okay? Whereas the breadth-first one, we're radiating out slowly. Okay? So the important thing to see is that there's 2 different data structures, 2 different traversal orders, and they make a big difference. Okay? Breadth-first search is going to be good for some things, depth first search is going to be good for some things. Okay? And the sole difference is the order in which we store them. The undiscovered vertices, the discovered but unexplored vertices. Any questions? Okay, there was a question a little earlier about different variations. How do you maintain the state of each vertex? Okay? We said that there were two flags. Another equivalent way to look at them is we can say that there's three states for a vertex. A vertex is completely unvisited, a vertex is visited but unexplored, or a vertex is completely explored. Okay? And in the particular pseudocodes we'll look at, they maintain these things by three different colors. A vertex starts out white, becomes gray when we first discover it, and becomes black when we've looked at all of its children. Okay? Any questions? Okay? What is breadth first search? Remember, breadth first search was the case where we were storing things in a queue. Okay? So how does it look when we actually implement breadth first search? Our algorithm is going to go something like this. For each vertex in our graph, we're going to start out, we have an input graph G and a starting vertex S. And breadth first search says, do a breadth first search from S in the graph G. What does the code look like? Well, there's first an initialization routine. For every vertex in the graph, except maybe the starting vertex, set its color to white. Why is that? Well, white corresponded to undiscovered. Okay, sort of the virgin state for that vertex. Okay, so the color of that vertex is white. There's going to be some supplemental information that we may or may not want to keep track of. We may want to keep track of how far is that node from the initial position of S. Because remember, what is breadth first search? We start from one vertex, and we're radiating out from that slowly. Here we can also keep track of the distance we are from our original vertex. Okay? Initially, we know nothing about the distance to our vertex, so we'll set it to be infinite. Okay? We don't know anything at all about it. Another thing that we can keep track of that turns out to be useful is the parent, okay, of each vertex. What is the parent? Well, I mean, if you think about it, we're now talking about graphs. There is no parent. If you say, look at a graph and you say, which is this vertice's parent? Well, that's not a defined thing. Okay? But we can define a relationship on our vertices where our parent will be the one that discovered us. Okay? So we can keep track of a discovery pointer, a parent pointer, that will point to, from the vertex that we've discovered, okay, basically will point to the person who discovered us. Every vertex will be discovered by exactly one vertex, except for one. Which vertex will not be discovered? The root, the one we started with. It was discovered because they gave it to us. Okay? Very easy to discover it. Okay? So we initialize the parent of our root to nil. The distance from the root to itself is 0. The color of the root, okay, that happens to be an S there. Again, it doesn't show up well. Okay? Originally, we color every vertex white except for the root. Why? The root has been discovered but not completely explored when we gave it to us. So it is in the limbo state. The root is gray. Okay? What do we keep track of? We have a queue that represents all the vertices that we have discovered but not yet completely explored. Originally, that is the start vertex. And this is the entire initialization. Okay, we now have a graph, we've set our flags, and we've set up our initial data structure of unsearched vertices. What is the point? So long as the queue of work to be done is not empty, means there's something there that we have discovered but not completely explored. So long as that's true, pick out the first guy from that queue, meaning the oldest element from the queue. For each edge coming out of it, Each edge adjacent to that new vertex. If its color is white, what does that mean? Each edge is going to be an edge UV. We're doing all edges from vertex U. If vertex V is white, what does that mean? We have a completely unvisited vertex. We have discovered a new vertex. What do we do if we have discovered a vertex? Well, we stake our claim, namely coloring it gray so nobody else gets to discover it, setting the distance to that vertex to be one more than the distance to us. Why is that? Here's the root. Here's U. Here's our newly discovered V. If it's 2 steps to get from the root to V to U, how far is it to get to V? Okay, 1 plus how long it took us to get there. Okay? More important, which is the vertex that discovered this new vertex V? It was U, because that's whose adjacency we're going through. We're now processing vertex U. So the discoverer of the new vertex is going to be us. Okay? And so we mark down who the discoverer is. Okay? If the vertex has just been discovered, we're going to eventually have to explore it, put it on the queue so we can explore it. Okay? That's what this is saying. NQ the vertex. Any questions? Okay? Suppose the color is not white. What else might we be doing? Okay? What color could it be? Gray. What does gray mean? It's been discovered, okay, which means there's no point to marking it gray because it's already gray. There's no point we can't change the discoverer as much as we might like to rewrite history, so that doesn't get changed. There's no distance. We haven't discovered a new way to get to it, or the shortest way to get to it. So nothing changes if the color is gray. Yeah?
But the distance may turn out to be shorter by the route you now use.
That's an interesting point, okay? But it turns out, actually, and we'll talk more about it later, if you're visiting the graph with if it's an unweighted graph, which is what we have here, a graph where each edge counts for a weight of 1, and if you visit it in a breadth-first manner, the amazing thing is that, in fact, the shortest path is the order in which you discover it. Okay? That's why breadth-first search is sometimes a good thing. Because, in fact, it's always discovering short paths to things. Okay? Okay, that requires a little bit to be convinced of. Okay? But that's true, and in fact, we'll get to it a little later. Okay? Any other questions? Okay? So once we have finished it, if the color was gray, vertex was gray, we didn't need to do much with it. If it was black, we didn't need to do anything to it. Okay? So only if it's white did we do anything. Once we finished exploring this vertex, the head presumably just copied the element out. We might as well take it off the queue. Okay? This basically just sort of copied out the first guy in the queue. Here we get rid of the first thing from the queue. Okay?
So this is at the end of the for each?
The end of the for each.
So actually the DQ should be a little bit...
Saying this thing should be here and here. Yes, it should be there and there. Okay? Again, it doesn't show up as well on the slide as I might like it to. Okay? Finally, we have this vertex. We visited all of its children now. In the course of this loop, we have checked out all possible adjacencies. We have thus explored everything associated with that vertex U. Once it's been discovered, everything's been explored going out of it, it is no longer a gray vertex. It now becomes a black vertex. Okay? And that's how we keep track of the colors. Okay, any questions about this? How many people follow the algorithm? How many people do not follow the algorithm? Okay? Let's look at an example, because it actually turns out to be a little confusing unless you look very closely at things. Here's a graph, and here is our initial state of that graph. What do we know? We have some vertex S that we've discovered, that we start with. we have a queue of things, okay, that need to be worked on. Originally, it's the only thing that's been discovered is S. This is the initial state of the vertex. What are we going to do in the course of our breadth-first search? We start out looking at all the neighbors of S. What are the neighbors of S? Which vertices? R and W. So what are we going to do at the end of that first step? We will have explored, discovered vertices R and W. If there was a distance of 0 to the initial start vertex, that meant there would have been a distance of 1 to R and W. R and W got pushed onto the queue. We first, in this case, happened to visit W, which is why it's at the head. We then visited R. That's why it's there. Okay? We now have a queue with our undiscovered, our gray vertices, okay, which have been discovered but not yet explored. Okay? And this is the work to be done. Any questions about that? What is the next thing that we're going to do? Which vertex do we explore next? You explore vertex W next. What happens when we explore vertex W next? Okay? Well, here's vertex W. Why did we pull out W instead of R? Well, it just so happened we pushed W in before R. Okay, why was that? Well, it happened to be first in the adjacency list. Yeah. It doesn't make a difference. It makes a difference in the sense that the order in which we visit things will be different. But the tree that we build will be the same. Actually, that's not even completely true. Okay? Okay, the shortest path, the length of the shortest path to every vertex will be the same. Okay? But the tree we build may be different. Because if we thought about it, suppose, let's say there was an edge. Let's say that we had an edge between V and W as well. If we had stuck R in the queue first, we would have visited V right after W. Okay? Suppose we had visited R first. Okay? Then R would prove to be the discoverer of V. If there had been an edge between here as well, if we visited W first, W would have been the discoverer of V. So the order will change who gets to discover what. Okay? But notice that if there was an edge here, there'd be two paths of length 2, shortest paths to S. So it doesn't really change anything significant, but it does change the structure of who gets to claim the discovery. Okay? Any questions about that? Okay? It's just like in the bandwidth problem. There's lots of different solutions that will generate the same thing. Okay? The important thing is that you find one of them. Okay? Any questions? Okay? So where are we now? We're now at this point where we visited vertex W, explore from W. What were the two possibilities? Where we discover T and we discover S. So T and S get stuck in the queue. Okay? Now we've completely explored this, completely explored that. Which is the next vertex we work on? R. Why? Because R is at the beginning of the queue. What will we discover when we visit R? We will discover vertex V. Okay? So V gets stuck at the end of the queue. Okay? What's the next vertex we're going to visit? Visit T. Okay? What are the vertices that we will discover from vertex T? U and X. Wait. U and X. Which vertex will we visit that we already discovered? W. Okay, because what is our state now? We're now at this vertex. We're now here. Now we want to visit all of the things that are adjacent to T. Well, U is adjacent to T. It's undiscovered. We have discovered it. X is adjacent to T. It's undiscovered. We have discovered it. X was already discovered, so it was gray. You're right. So here's a case where we have three neighbors. One white, one gray, one black. We will visit each of these. Okay, although, there's not much, we're not going to get any benefit from here, not going to get any benefit from here, but here we get credit for discovering somebody. And the graph we get now looks like this. Our undiscovered guy gets stuck on the back. Any questions? One lower?
The U got stuck on the back. And the T is now black.
You, right. Okay. I'll believe that. Okay. Now what's the next thing we do is X. Where is X? Well, why is X? Well, we discovered X before X was at the head of the Q. We will visit 3 vertices, black, black, and white. So Y is going to get stuck at the end of the Q. What's the next one we do? V. What's V's neighbors? V's neighbors are black. So what happens to the Q? It gets shorter because V gets deleted and nobody gets Q. Okay? Which vertices do we visit from here? T, which is black, and Y, which is gray. We've already discovered it, so nothing happens here other than the Q gets shorter. Now we visit Y. What is Y? Well, it's got 2 edges going out. Okay? One of them goes to black, the other goes to black. So we haven't discovered anything. Our Q is empty, and our search is done. We have visited each edge twice. Okay? We have discovered anything there is to discover. Okay? And we have not gotten trapped. Any questions about the breadth first search? Yes. The question is, if we have a vertex on the Q that's got only black or gray vertices, is it completely explored? The answer is no. Okay? You want to make sure you walk each edge in both directions. Okay? Take a look, for example, here. I mean, in this case, it's important to walk through each edge in both directions. Why is that? Because that way we know that first, we're not getting cute. We have a nice, simple algorithm. Okay? We're making sure that we don't get lost. We don't forget to visit something. The cuter you get is the more likely you're going to have a condition that's going to be wrong. This is a fairly subtle thing. Okay? It's surprisingly subtle. Okay? It's very easy to come up with a variation of this which doesn't visit everything, or it gets trapped into a cycle. So my reaction is, don't be cute. Make sure that you visit everything explicitly. It costs you nothing. Because visiting each edge twice is the same as visiting each edge once. We're in a big O world. And even if we're not in a big O world, if your program, the slowest thing in your program, if the slowest thing in your program is you're visiting each edge twice, you're in good shape. Okay? That's not what's going to hurt you. Okay? What's going to hurt you is you're going to get trapped. You're going to make mistakes because you get confused. Okay? And that's what we're avoiding. Any questions? Okay? So that is breadth first search. The alternative, we said, was to store things in a stack. And that is depth first search. Okay? Now, we could go through a version of depth first search that is exactly the same as breadth first search, only instead of, if we took a look at this code, if we wanted to change it to a depth first search, one thing you could do is simply replace the NQ and DQ operations by push and pop. Okay? And that will work. Okay? Turns out the distance restraints won't have any meaning because that distance property that we were assuming isn't going to be true with depth first search. Okay? But it turns out that when you're doing depth first search, the usual way to do it is with a very slick recursive algorithm. Okay? If you don't understand the recursive algorithm, go back to the breadth first search algorithm, add the push and pops instead of the NQs and DQs, and see if you can make it work. Okay? But the recursive algorithm is a little slicker, okay? And just turns out that it's good to make sure you understand both. Okay? How do we do it? Well, first of all, with depth first search, that distance constraint that we were talking about turns out not to be very interesting. Okay? Because remember, we're going to be starting from one vertex and walking as far as we can away from it as quickly as possible. So the distance we get to a vertex is more likely to be long than it is short. Okay? It's just an intuitive argument. There's no reason to believe it's going to be short. So this distance is not worth maintaining. But what turns out to be sometimes useful is to maintain the discovery and final exploration times. Okay? What time did we color a vertex from white to gray, and what time did we color it from gray to black? That will turn out to be useful. Why? Well, if you think about it, we'll see. Okay, let's say we'll see a little later why it's useful. Okay? But it turns out to be sometimes isn't. It turns out not to be any harder to keep track of. So what do we do in breadth depth first search? First of all, we have an initialization phase. Every vertex, okay, is going to be originally colored white. What's the parent of every vertex? Well, initially it has no parent. It's not been discovered. We don't know who the discoverer is. The time that it was discovered, well, that's 0. The original total time in the execution is 0 originally. The discovery and finishing times are initialized to 0 as well. The key step from this, outside of initialization in our recursive program, is we're going for every vertex in the graph. If that vertex is white, we're then going to do a depth first search from it. White, remember, meant undiscovered. Okay? How many times are we going to be doing a depth first search visit from within this loop? Okay?
The graph is connected only once.
If the graph is connected only once, what is the idea here? In this case, we're going to want to visit the entire graph. If the graph looked like this, there's no way of getting from here to here. There's no way to do it in breadth first search either. There's nothing magical about that. But in this version of depth first search, we're going to take care to visit every vertex in the graph rather than every vertex from a starting point. Okay? There's no reason why we didn't, no particularly good reason why we didn't do this from breadth first search either. Okay, so don't get confused about that. But what we're going to do is for every vertex that's undiscovered, we're going to do a depth first search visit. So what happens? You start out with a graph like that. You happen to start walking from here. You will discover and blacken every one of these vertices. After you finish that depth first search visit, everything here is blackened except for all of these. So you now go through all the vertices. Is this guy black? Yes. Is this guy white? No. White, no. White, no. White, no. White, yes. So I'd have to do another search from here, and that's what's being maintained out there. Okay? What does a depth first search visit routine look like? This is where the recursion comes in. Okay? We're doing a depth first search visit from a particular vertex. We called it when the vertex was undiscovered, correct? It was white. Now that we're calling it, it has been discovered. Its time has come. So it's now colored gray because we have discovered it. The discovery time is now. So we say that the discovery time for that vertex is the current time. We increment the time to show that the time has advanced in the future, so we don't discover two things at the same time. Okay? What do? For each edge coming out of this vertex, or each vertex that's adjacent to you, if the color is white, then we have discovered it. If V is white, what is the discoverer of it? You. That's the one that we're currently processing. So we now have claimed that it's discovered, but now immediately start visiting it. Okay, this is the difference between the stack and the queue. In the queue, we said, when you're discovered, you go to the end of the line and we wait for it. If not, the moment that we have discovered it, we're going to start exploring from there. Notice we haven't finished exploring all the edges adjacent to you. The instant we start discover, we discover a new vertex, we start exploring there. Okay? Which vertex has a finishing time that's earlier? The parent vertex or the child vertex? The child vertex. Why is that? Because as soon as we have a child, we say, you finished your job. And we're not going to get returned from this recursive call until that guy has finished, the child has finished exploring everything. That's the purpose and meaning of this recursive call. So only after all of our children have discovered and finished exploring everything associated with them, only then can the parent rest. Okay? The parent now setting its color to black because we visited finished exploring all the children. The finishing time is now. And again, we update the clock for that. Okay? Any questions about that? Okay? The important thing is to see how the recursion works. If you understand how recursion works, it's not that confusing, or you can work your way through it. Yes?
I'm probably missing something really simple here. Why are you setting the clock the first time if you're going to set it on the tail?
Why are you setting it on the first time if you're setting it on the tail? The reason is because something different has happened since then. There's a discovery time. We want to make sure all the discovery and finishing times are different for every vertex, that there's a different event. The time is going to represent an event. One vertex will be either discovered or finished at each time step.
Yeah, but when you come out of the recursion...
When we come out of the recursion here, the finishing time is going to be this time plus how many things have been discovered and finished since then. So realize that somehow the time is a global variable. Okay? That's why we're doing it that way.
Can you say Brad first search is more efficient than DFS?
Is breadth first search more efficient than DFS? The answer is no. Okay? Because how much time does breadth first search take? How many times do we visit each edge? How many times do we visit each vertex? Well, potentially for every edge there. But we're visiting each edge twice in breadth first search. We're visiting each edge twice in depth first search. Both of them take order n plus m time. There is no efficiency difference that's worth measuring, okay, in the big O notation. Okay? And that's how we keep score. And in practice, there's no big difference. That's not where your win's going to be.
Yeah, but
okay.
you use recursion.
So you use recursion in this. Recursion is not where the big win is. Okay? It's not going to cost you that much. Okay? In fact, so don't worry. I wouldn't worry about that. Okay? If you discover in the bandwidth programs, you'll find that the recursion didn't slow you down. It's not as big a loss as you see.
Recursion may be programming where run out of memory.
Okay? There's a concern about running out of memory. In fact, maybe that's actually not as much of a concern. There's actually a good reason why usually depth first search actually uses less space than breadth first search. Because in some sense you usually have fewer, it depends upon the graph. There's a case that can be made that in a lot of cases actually depth first search uses less space than breadth first search. Okay, but I don't want to go into that right now. The main reason is because you're walking down to the end of the graph quickly, as opposed to sort of, if you have a graph that you're exploring everything in a broad way, you eventually have almost everything in the graph in an undiscovered but unprocessed state. So the queue would expect to be maybe larger than you might get in a depth first search graph. Okay, but that's not an issue. That's not an issue worth fighting about. It's not the important thing. Any questions? What's an example of depth first search? Okay. Here we have a graph. And here it is a directed graph. What does that mean? Well, the edges are only going one way. Okay? We can use either breadth first search or depth first search on directed graphs or undirected graphs. That's why we talk about the general algorithm visiting both ways. If it's an undirected graph, we visit it both ways, the edge both ways. If it's a directed graph, we'll only visit each edge the way it's supposed to be visited. Okay? What happens when we go through it? We start out at some vertex. The discovery time of this vertex is 1. Why? This is the vertex that we discover. Our stack will only consist of this. What is the things it's adjacent to? It's adjacent to V and it's adjacent to X. Which vertex do we visit? Well, let's say we happen to visit V. We have now discovered vertex V, okay, and we now interrupt what we're doing. We had U on the stack, okay. Now we go and visit vertex V. V, we look at the edges going out of V. Well, there's one edge going out of V. So we push V on the stack, and we interrupt what we're doing. And now we've discovered this. Which edge goes out of V? Well, there's one edge that goes out of V. Edge X. okay, and edge x, vertex x. So if we discover vertex x and we add that to the stack, what do we do from here? Well, we now have an edge that goes between us and a vertex we've already discovered. So do we add this back to the queue, back to the stack? No, we just sort of look at it as it goes by. Okay? Now we've finished exploring here, we back up. We now go back to y. We finished looking here. Is there anything else coming out of here? No, we're finished with y. We go.
We got that by putting a 4, a 5, and a 6 in the finish.
Oh, okay, right. So the time that we finished this thing, we're now finished with this vertex. This becomes a finishing time of 5. Okay? We're finished with this. This becomes a finishing time of 6. We back up from here. We're back up to this vertex. Are we finished with it? Yeah, there's nothing else going out of it. That finishes at time 7. Back up from that. We're at u. Is there anything else? Have we finished with u? Okay, yes, that is a finishing time of 8. We delete that from the stack, and now we're at the world that looks like this. We finished doing this. We keep backing up, backing up. We now have a state of the world that looks like this. Okay? Any questions about that? I may have gone through the movie a little quickly. Now we're at this situation again. Which vertex do we pull out next? Well, it depends upon, now we're in the outer thing outside our recursive call. We're now in that loop that says, well, is this vertex white? Is it white? Is it white? Here's one that's white. We discover vertex 9. Let's say W is the one that's going to be the one we pick. So we discover 9, W, color it gray. Its discovery time is 9. We look at all its children. This edge is going back to something we've already discovered. Okay, so that's no longer interesting. This discovers something new. That's vertex 10. That vertex gets labeled as discovery 10. We push W on the stack. Look at this Z. From Z, we explore Z. What are the possibilities of Z? Well, there's an edge we have to go through. This edge sort of goes back to itself, but that's it. Its finishing time is now. We back up to the parent, okay, and lo and behold, we get back to this guy's discovery time is now 12. The finishing time, if I can find it here, is 12. Okay, any questions?
Am I getting this wrong, or is it that breadth first search can do two disconnected graphs in the?
No, breadth first search cannot do two disconnected graphs. Okay, breadth first search can be modified to do two disconnected graphs by simply adding this extra portion to it. Here was a depth first search visit. We had the equivalent of a breadth first search visit from a vertex. The other thing that we added here was that we went through and made sure we visited everything that was white eventually. If we add such a component to breadth first search, it would do the exact same thing. So that's not a conceptual difference. The conceptual difference is the order that we visit them in. Okay, any questions? Okay. This may be, again, once you see it, it's very, very simple. I went through that in a little bit more detail than I might have normally done because it's not as simple as it looks. Okay, I saw a lot of people walking out now. Okay, it's not as simple as it looks. Okay, but what's interesting about it is that there's different properties to the trees that we build. If you think about it, whenever we did one of these traversals, be it breadth first search or depth first search, there is a tree, if the graph was connected, a tree being formed, okay, on the vertices of the graph. Why? Well, we started from some root, and if we keep track of which edges that we discovered, certain edges were used to discover other vertices. Since every vertex got discovered once, okay, there are no cycles in this graph, okay, because well, let's just see if we can come up with a quick argument for why that is. Well, if you discovered a vertex, if you were coloring these vertices in the order you discovered them, since you're always coloring a white vertex when you discover it, the only way you could have a cycle is if you colored an edge that had already been discovered. Once you color a vertex that's already been discovered, that's not something that you're discovering again. So there's no cycles. The thing has to be a tree. These trees have different properties for breadth first search and depth first search. That's the key to understanding them and the key to making use of them. The property of the breadth first search is that this tree always, always, always reflects the shortest path between the root and each node. Why is that? Well, let's take a look at a tree that we're doing a breadth first search on. Okay? We are exploring the vertices in the order that we're discovering them. Okay? So we're not going to explore any vertex until we've explored any vertex which took 2 units to discover, until we had explored all the vertices that were within 1 unit of discovery. So starting out initially, the root is clearly the shortest path to the root. We're now going to visit all the edges that can be reached in 1 unit from the root. Okay? Clearly, that's the shortest possible path to all of the vertices that we just discover that are directly connected to the root, if we have an unweighted graph. What is the next vertex we explore? Every vertex we now visit, the next vertex we're going to now visit is going to have a distance of 1 to the root. Okay? And we're not going to visit any vertex that's a distance 2 to the root until after we've completely explored everything that's a distance 1 from the root. So the important thing to see here is that we're building these things in the order of distance. Okay? That's the property of this. Okay? Further, okay, any questions about that? Let's just make sure. What other edges can there be in the graph? Okay? So for example, let's take a look at this thing. Could we have an edge going, when we look at when we do our breadth first search, could we ever have an edge from a vertex that is white to a vertex that is black? Okay? Well, let's think what that means. Here we have a black vertex, meaning we have completely explored all of its children. Correct? Is it possible that we have a gray vertex here? Could we have a gray vertex go, when we first discover it becomes white, it goes to gray. From gray, could it go to black? Well, it could, because we're going to be visiting each edge twice if it's a directed graph, an undirected graph. Okay? So the answer is that's certainly possible because we'll catch it on the return. The more interesting question, could we have an edge that goes from here to here? Okay? Could we have, or let's say put it this way, if we have an undirected graph, could we have an edge that goes from here to here? Okay? My claim is we can't. What does that mean? Well, this vertex here, the shortest distance to it was 1, 2, 3. The shortest distance to this vertex was 1, 2. It's 2 if we go through this vertex. If we had done a breadth first search, what would have happened? Discover, 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 discover. Explore all of this node. We would have discovered this node not off of here, but off of here directly. So any edges in this tree are going to be all the red edges are going to be ordering the shortest discovery. The important thing to see here is that all other edges in the tree have the property that they go to either edges on the same level of the tree, other vertices on the tree, or they go at most 1 level ahead. Why is that? It's because we're plotting them in the order of shortest distance. If there's a vertex going to be on the 4th level, 1, 2, 3, 4, that means that it was discovered at the shortest path is a distance of 4 away from it. That meant that there had to be no vertex. It could not have been adjacent to a vertex of distance 2 away. So the thing about the breadth first search tree is it reflects the shortest path structure, and all the other edges basically go between vertices of one level and vertices of the next level, or the same level as before. Any questions about that? Okay. Depth first search. Depth first search trees have another property, okay, that's different from breadth first search trees. They have nothing to do with distance. However, in practice, depth first search trees actually turn out to be more useful than breadth first search trees, at least as far as designing algorithms. And the reason why is because of the following property, okay, which may seem a little bit obscure at first, okay? But the interesting thing about depth first search is that it organizes the edges of the graph. If we have an undirected graph, a depth first search is going to organize the edges so that every edge is either going to be a tree edge, okay, meaning it represents an edge of discovery, or it goes back to an ancestor in the discovery times. Let's look at an example just to see what I mean. Here we've got a graph, vertex 1. Let's do a depth first search from it. What's going to happen? We start from vertex 1. We discover a new vertex 2. We start from 2. We discover a new vertex 3. From 3, we discover a new vertex 4. From 4, we discover a new vertex 5. From 5, what vertices do we have? Edges, well, we go back to 4, which is direct. Or we discover a new edge that goes from 5 to 1. Notice 1 is an ancestor of 5. Okay? From 5, we can go back to an ancestor. 2, okay, 5 goes to 2. 2 is another direct ancestor. My claim is if you have an undirected graph and you do a breadth first search on it, every edge has to go between either a tree edge or goes back to an ancestor. That we're going to call a back edge. Okay? And the reason why depth first search is useful, okay, is these subtle properties. Okay? The fact that we're organizing the edges into one of two classes, tree edges or back edges. That's the power of depth first search on an undirected graph. Okay? Any questions? If you think about it, it's got a nice ordering to it. Okay? Let's take a look at this edge. Could there ever be an edge, if we have a depth first search tree like that, could there possibly be an edge like this? If it's an undirected graph? Well, is this a tree edge? Is this an edge, a back edge going to an ancestor? Okay, no, this is not an ancestor. This is our uncle, not our brother, not our parent or grandparent. This could not happen in a depth first search of an undirected graph. Why is that? Okay? Suppose we were starting from this vertex 2. We were doing a depth first search. Bop, 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 bop. We discover, back, back, back. We would now investigate all edges coming out of this vertex, correct? If it was an undirected graph, if there was an edge from 2 to 6, there's an edge from 6 to 2, correct? When would we discover vertex 2, vertex 6? Well, let's say, okay, if there had been an edge from let's put an edge from 2 to 6. The key point is that 2 will discover 6 before 1 will discover 6. Okay? So there could not have been a cross edge like this.
So the edge goes in the other direction? And
No, the edge,
from 1 to 6.
if it was an undirected graph, if we had discovered this edge, what would the tree have looked like? 1, 2. 2 would have discovered not only 3, 2 would also have gotten credit for discovering 6. So the tree would look something like that, and there would not be a vertex. The 6 would not hang off of 2, it would hang off of 1. So the interesting thing here is that if we have an undirected graph, okay, in the depth first search tree, okay, we can assign a direction to each edge. It's either going to be a tree edge or a back edge. Okay? Okay? So in a DFS of an undirected graph, every edge is either a tree edge or a back edge. Okay? Yes?
So if there are no back edges, then the graph has no cycles?
If there's no back edges, the graph has no cycles. Is that true? How many people think so? If I have to do a depth first search of a graph, and I have no back edges, if it's an undirected graph, can the graph have any cycles in it? Okay? Not if there's no back edges, because everything else is a tree edge. Trees don't have any cycle. So how do you test if a graph has a cycle in it? You do a depth first search, a breadth first search, either a depth first search. If you have any back edge, it is going to be that means it created a cycle. Okay? Turns out you could have done the same thing with breadth first search. Because if you have a breadth first search and any edge is not in a tree edge, that also means it's a cycle. Because the only thing that's not a cycle. Okay. But on the other hand, what's good about this is it tells you what the cycle is. Okay, you know that exactly the chain has to be all your ancestors, whereas things might be a little bit more muddled in a breadth first search. Okay? If you have a directed graph, what does the traversal look like? Okay? In a directed graph, you have no edges. You cannot have, things get a little bit more complicated. Okay? But the important point is that there's going to be no cross edge. Okay, if you think about it, we've got edges that correspond to tree edges. There's edges that go back to our ancestor. What are, in some sense, some other possibilities if we didn't know what we were talking about? We could have had edges that go back to cousins. Okay? Okay? Or brothers. Not with a depth first search of an undirected graph. But what if we had a directed graph? Suppose there was a directed edge from 6 to 2. Would we have discovered that edge when we were visiting 2? No. So with a directed graph, it's possible that we have cross edges. But these cross edges are going from right to left, from newly discovered vertices to older discovered vertices. We cannot have a cross edge that goes between a higher numbered vertex or to a rightward vertex. We couldn't have a cross edge that went like this. Why is that? Because if 4 would have discovered it, what would 4 have done with it? It would have stuck this hunk of the tree down there. So the important thing is that each edge of a depth first search tree is going to be classified. Okay? But there's fairly tight conditions into which way an edge can be classified. It can be an edge in the depth first search tree. That's what we call a tree edge. It can be an edge that goes back to an ancestor. That we call a back edge. In an undirected graph, those are the only things that can happen. In a directed graph, we might have the possibility that we have what we call a forward edge, namely an edge from a vertex to a descendant. Okay? How could that be? Well, suppose we had done our search and we started here. We search, 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 discover. We now finished, we haven't finished, we discovered this vertex, but we haven't finished exploring this. When we finish exploring this, we might discover everything else. Okay, and that would be a forward edge. Okay? Finally, cross edges, we can have vertices and edges in a directed graph that go from right to left. Okay? But we cannot have edges that go from left to right. Okay? The important thing of depth first search, and this is the lesson, okay? The thing to file away about depth first search is that it is ordering the edges of the graph into a small classes. For undirected graphs, this is all we have. Okay? For directed graphs, it gets more complicated. But even there, it's simpler than it would otherwise be. Starting next class, we'll see how this simplification can lead to faster algorithms. Are there any questions about it? Okay, thanks a lot. Pick up the assignment. We'll talk next class.